All right. Hi, everyone, and thank you to Joaquin for inviting me out to give this talk. I'm here at the epicenter of data visualization at its apex to talk to you about situations when data visualization isn't enough when illustrating astrophysics for the public. And I apologize, I realize I never changed. You know how we always copy the old talk and then we revise it for the new thing, and I forgot to get rid of the old thing because this should say NCSA down here. I actually have a lot of new stuff from that previous talk. But so I'm no talk about visualization this week. Can start with anything but the eclipse. So yes, I got to see it. I was down in Dallas. These are some pictures. But I would say that basically this is here to prove that I reached tier 3 of the XKCD scale of eclipse visualization. Yes, I made it up through the reaction shot, but my fancy lens threw up an error message 10 minutes before the actual eclipse, so I just decided to watch it instead. But I would say that what the eclipse really told us was not our nature in terms of researchers, but something more internal to ourselves. Yes, I think we all discovered our tastes are very singular, especially when it comes to the kinds of astrophysics that we want to see with our own eyes. So a little bit about me. So I'm an astronomer. Oh, thank you so much. I'm an astronomer. I work at Caltech IPAC, which is a science and data center for astrophysics and planetary science at Caltech. I started in a traditional career path. Well, I mean, running back, go back to my early childhood, probably the two key inspirations were a combination of Star Trek, original series, and Cosmos, sort of hitting both sides of astrophysics. It was always my love. By the time I got to grad school, I was trying to do something more practical than astronomy, but just gave up and realized astronomy was what I loved, went into that track. I went through a couple of postdocs, then worked as a staff scientist at IPAC on the 2-micron all-sky survey, but then made a transition. I had an opportunity to shift into a career path I hadn't really imagined, which was that of visualization scientist. And in that role, I've had a remarkable opportunity initially to work with NASA's Spitzer Space Telescope, the fourth and final of NASA's great observatories, and the infrared telescope that has really set the stage for the science that is now being carried forward by NASA's James Webb Space Telescope. But in the years that I was starting on Spitzer, I then had an opportunity to work with more and more amazing astrophysics missions all across the spectrum, GALEX, NEOWISE, Herschel, NuSTAR, and then more recently have been supporting more and more of the communications efforts by Caltech-led groups, including ZTF, LIGO. I got to participate in helping communicate the first LIGO results and the second Event Horizon Telescope results. And I amazed what I've gotten to connect to. My work initially was much more data-focused, the rendering of data as imagery, as we see sort of to the left here. But as time has gone ahead, I spent more and more time shifting into my hobbies of illustration and bringing that forward to help tell science stories through visual means. Because in many cases, especially early in Spitzer's mission, data could tell enough of the story to interest you in what the result was. But many times we have to admit data needs help, especially when data gets to a point that it even only necessarily communicates clearly to people in a very narrow silo who work in that field directly. If you have ever done exoplanet work, you might recognize a transit image, a transit plot. But someone might look at that and think it's a spectrum. So yeah, we need to do other things to help communicate this. So astronomy illustrations do serve two really key purposes here. They both inspire by getting people excited about a result, and then if they are successful, they inform. They tell us something about that result specifically. I actually had a chance to dig back a while ago to some of my early work. I rediscovered, I believe, my first attempt at illustrating a galaxy, and circa 1979, yeah, I'm that old. When I looked at this recently, rediscovered this recently, I was kind of horrified, thinking that doesn't look anything like a galaxy. The morphology is completely wrong. But as I thought about it, I realized that it was kind of a consequence of what I saw as astronomy imagery at that time. At that point, images of galaxies were exposed on photographic plates, and almost always overexposed so that the cores were burned in to bring out the fainter outer structures. And I realized that had led me to a misconception of really not understanding what the core of a galaxy was. Something that now with modern data sets, like the Spitzer image, right, we now know how centrally concentrated stars are in the center, how much brighter they are. But this led me to realize how important visualizations can be in affecting our mental geography of the universe. And I decided it isn't even an even artwork situation, but especially in artwork. Because artwork is our avenue to show people things that we don't have direct data to reveal. And if we do that well, we can help build a mental geography of things that have yet to be revealed through direct imagery. So the kinds of communications we do when we reach the public, I think, span a spectrum that is related to the nature of the audience and how much hold you have on them. On one side, we have education and classroom, formal education. And this is a kind of prearranged, facilitated situation where people don't necessarily have the freedom to go to the door if they get a little bored. So you have a bit of leeway in walking through a visualization. You can give them a curated experience. In the middle, we have informal education, museums, astronomy events, where people have gone out of their way to go, so you have a little bit of their attention. But you still are trying to pull them in. You still have to engage them a little extra. And then in the area that I work most in, communications, where it's press releases, news media, we are fighting for attention because a press release from a NASA mission is right up there with speculation on whether there will be a Guardians of the Galaxy 4. And if we are not fighting to pull people into the story, the eye will just glaze over to the next news story and they'll miss what we do. So there's sort of a threefold purpose that I see that a piece of astronomy illustration needs to accomplish in the context of science communications. One, of course, is to grab the attention. Then, if we can, illustrate a basic concept that as they go into the article will give them context so the article will have more meaning right at the start, right? If you can preload a little bit of the concept in their head from the image, then they will get more out of the story and hopefully engage with it much more deeply than they might have if this had just been a headline. This also got me thinking about what I initially thought of as a data art continuum, and where like on one side you just got pure science data and on the other side pure aesthetics. But I realized when I was trying to turn this into a talk topic that this is a little oversimplified, and I actually decided that this really had to break down into at least two axes. One being the level of science content and the other being the level of visual engagement. And then, of course, at one end, we can place the data that you might put into a research paper that doesn't necessarily have to be super engaging because you're really focused on communication of a technical result to a technical audience. On the far other side of this graph, we can place Guardians of the Galaxy, which is really cool, but is not going to teach you one iota of astrophysics. It's very colorful, though. Did have fun with that. Then we can maybe write there, note there are things that have neither content nor engagement, but, are entertaining for their own right. And we can spend all day having fun now with this graph, placing various things where we think it might fall. But the area that I want to pull attention to is up here in the area our practitioners often call astroviz, where we are really striving to maximize both of these as much as we can for the purpose of science communications. So how might you evaluate a science visualization of being effective? Well, there are several ways, of course, you can. You might ask the question, is it accurate? Is it really telling something that we know is real? Is it amazing? Is it like, did you just see it and want to know more about it? And another question you can ask is it clear? If you're actually trying to get a point across, it's maybe not enough to be amazing, you have to be able to follow a thread through the communication. And this actually maps into, I think, what are three voices that need to be at the table every time when developing astronomy visualization. What I sort of have dubbed the Astroviz triad: science, art, and communication. And each of these are different expertises into a different way that we are, a different part of the total picture we're trying to get together. And what we have found at the Spitzer Science Center and IPAC over the years, the most effective process that we have come up with for doing this is to really have all of these voices at the table at the time you are working through the visualization. You want the scientist to be able to answer questions from the artist, and you want the communication specialist to be able to actually remind people of like the target audience and the goals and the core idea that you're trying to get across. And it is in the ability to kind of hash through this around and around that finally the artist can go away with a clear picture that will achieve the maximum communication, where you don't get the scientist suddenly saying, oh, that's not all what I thought, right, if they weren't engaged in it. Or I've seen a lot of situations where it's more of a linear process, where the communication specialist talks to the scientist, decides what the story is, and then tells the artist what to do. And again, these are all modes that lead to not necessarily failures, but much more revision, many more cycles when you play a telephone game where it falls apart. And I think that really it's important to have active advocacy at all points. Now I have an interesting career because since I came from science, but now I'm doing the art, I sort of can, sometimes I have played the part of being communicator in these conversations, working with an artist, talking to the scientist. I can sometimes play translator back and forth between the two because I know how both speak, and that's been very helpful to me. Another way that I have decided you could kind of visualize the visualization process is thinking about just sort of this abstract space of any given science result has sometimes a very small number of really known facts, results that are in there. There are, of course, a lot more things that we know to be false from that result that you can absolutely rule out, and even more things that are simply possibilities, hypotheses, things that are consistent with, neither excluded nor supported by the result. And in order to do a piece of astronomical art, you basically have to just grit your teeth and draw a circle around some of this. You have to choose which of the known facts that you're trying to really bring forth in the art. You have to just embrace a subset of the possibilities, because you can't draw an illustration of an exoplanet that both has an atmosphere and does not. You make a choice and pick one, and that's what you go with. And even sometimes we will encompass some known falsehoods in there too. Things you know aren't true, but may actually be useful in the service of communication. A very simplistic view is maybe exaggerating the relative scale of planets so that you can see distant members of an exoplanet system as part of the communications goal, even though they might not be that large, really, if you were there. So, but what's interesting is if you look at, and then once you've drawn that circle, everything that fills the gap between that's the art. That's where the artist comes in. You make the choices. You fill out all the pixels of the image with something that you've done. But what's interesting about that is that in filling in those gaps, taking the art plus the possibilities you've chosen to illustrate, a colleague of mine at a plenary talk at the AAS had stated some years ago that he saw that as equivalent to a hypothesis, right? You've chosen a particular thing that you are going to represent, which may or may not be borne out by the results as you go further, as you learn more about it. But, it's a testable hypothesis. Is there water on this exoplanet? We've shown a hypothesis that there is. Someday we might find out it's true, or we might invalidate that and move forward. So I'm going to step through a few case studies of things that I've done over the years. And first one is the Milky Way, our own galaxy. Of course, you might ask fairly, why do we need to illustrate the Milky Way? Because it's literally around us. We have more data about the Milky Way than anything. But I will challenge you to think about it in these terms. If you were to just find yourself standing in the middle of Times Square and being handed a piece of paper and say, draw a map of Manhattan, you would be rather challenged, right? You have certain sight lines where you can be very sure that you're doing a pretty good job. You have a lot of other regions that are blocked. You see some tall buildings. You can speculate, and it gets very, very sketchy after a while. And that's very much the situation we're in the Milky Way, because so much of what we see doesn't have a clear distance assignment to it, and so we have to make a lot of guesses. So back in 2005, we had a Spitzer release come out that had a really interesting science result that I did this illustration to support. And the science result was really focused on the size and orientation of the bar in the center of our galaxy. And even to this day, it is not very well known, even sometimes in formal education communities, that we live in a barred spiral, not just a regular plain spiral. And so in this, there were really three elements that were the check marks that went into this. The size and orientation of the bar relative to where the sun is, and the fact that the Milky Way itself is a spiral galaxy. And so we put this out, and the release was, got a lot of traction. But interestingly, I was stunned how much traction it got. This actually started appearing everywhere. It was in other news stories. It was showing up on art sites so you can print it out to put in your living room. It was everywhere. I saw it in the... Pardon? Every textbook. Forget the textbooks. I found it in the Sci-Fi Museum in Seattle. Like, this was amazing. But Bob Benjamin and I, who had worked together on this initial release, we both were like, oh my God, we didn't actually try to work out like the rest of the Milky Way. We were really just focused on the bar. And I also started to get the science papers. Oh, you missed my science result where this particular arm should be. Oh, you didn't. Did you notice my gas map? And I'm like, crumbs. Okay. Bob and I were both like, we really need an excuse to fix this, and soon. So it turns out Bob actually did have another good science result in a couple of years, which resulted in this updated version of the Milky Way. And some of you may have seen this. This has also gotten a lot of traction. His particular result had to do with star counts along the Sagittarius arm and basically not finding an excess of stars that we would normally expect to see along a tangency line there. And so, but that gave us an opportunity to revisit this. But moreover, it actually inspired Bob to go and plan a special session at the summer AAS meeting on Milky Way structure, specifically to bring together a lot of different disciplines that often don't talk to each other. The maser people, the H1 mapping people, the stellar count people, the molecular gas, millimeter wave, and try to all get together and compare notes. And so Bob actually accumulated a tremendous amount of information from all the people coming to that special session. He and I worked through it. We sort of made decisions on relative scales and how to get everything to line up. And once we agreed upon that layered set of data sets, I sat down, and by that point I had 2 days to paint this out in Photoshop. And we had a few things that are real in here. Like there were actually, when you see the little H2 regions in there, 16 of them actually correspond to very well-known positions of maser sources that radio astronomers gave us on unpublished results that actually took about a year before they were peer-reviewed and published. And interesting enough, when their press release came out, they were able to use this image, and they were all on the map. Wow, how fortunate. But because this time we had done the work, we put a version out with a grid, distances, we labeled features, and this was at least more what we wanted there to be. And as you know, and like you say, I think a lot of you have probably seen this. It's gotten a lot of traction. And I'm proud to say that, and I should say, a decision we made early on was to make this a complete piece of artwork, even though we didn't have data. Like, as you know, there's a zone of avoidance behind the galactic center, where velocity fields are basically null. A lot of degeneracies. But we both agreed, instead of trying to make this just based on the data, it was important to just have a complete picture to inspire and fill it in as best we can. But what's cool about this is there are actually 3 features in this art, 2 of which I've marked here, that were subsequently discovered in data. And in particular, one of them, colleague Thomas Dame, when he found had a new H1 gas result where he had mapped out a new spiral arm, a far H1 arm. When he laid it, he was using this image to sort of lay it out to have a reference point. It was so closely correlated to that. I got this desperate email from him asking, did I build this using a data set that he needs to reference? Is there another group working on this? And I was like, relax. You are just, all you have to cite is artistic balance and symmetry arguments, because I just used my best artistic judgment and what we know about logarithmic spirals and things to extrapolate that. And in that sense, I think this does kind of validate, again, the sense how art can act as hypothesis, as science hypothesis. So another case study, something that we actually get a lot of science results we communicate, is black holes. And this is something that has been represented very creatively in pop culture over the years. Sources dating back to the 70s, even Cosmos 2 had it, but none of these are actually right. In fact, if you sort of look at historically how we've represented black holes in pop culture, they fall into three categories. There are the bowling balls, there are the bathtub drains, and if you are J.J. Abrams, they are flat, swirly things with lots of lens flares. So why is pop culture so off base on this? Well, honestly, we can point right back to science visualization for this, because it's kind of mostly the same. I've done my fair share of bowling balls over the years, I admit it. Bathtub drains are common, and in fact, even understandable, because frankly, we use these space-time diagrams to show, gravitational deflection through a fourth dimension, which looks a lot like bathtub drains. So of course, people illustrate these like that. But we've known for, over a century now that black holes warp light. So why do we never see lensing as part of our renders? Well, for one thing, it's harder to create. And particularly when you're working in the press release realm, meeting deadlines trumps doing things correctly. So you sometimes have to cut corners. But another interesting pushback that I have felt over the years is that lensing was not expected by people. People were used to seeing the bowling balls. There are press releases where we were developing, and I was building graphics to show at least some quality of lensing, and I got a lot of pushback from the media office at JPL, like, well, what's going on here? This is confusing. It's like, yeah, but that's what it does. It's like, well, people aren't used to seeing that. Well, maybe they should be, and we have to fight and negotiate this sense of expectation. Now, I will say I did manage to have some successes in there. Actually, a colleague of mine, Tim Pyle, produced a web episode, Spaceship Spitzer, in 2008, which was visiting a black hole. There's a little bit of Star Trek. Michelle Fowler, if you've seen her in any science videos, was in there. And when he was doing this, I was saying, Tim, you've absolutely got to show some light warping around that. And he was like, this looks confusing. I don't get it. This is not what people see. And I worked really hard, no, but no one's done it. You'll be the first. And fortunately, Michelle was on board with doing it, so he did it this way. So I believe we were the first science video ever to show light warping around black hole. I may be wrong, but I've not seen another one since. And occasionally I was able to do it in press releases like the Spitzer one. But that changed in 2014, though, right? There's this little thing called Interstellar. Director Chris Nolan, scientist Kip Thorne, visualization consultant A.J. Christensen. And at this point, you had a Hollywood movie that doubled down on wanting to do the visualization of a black hole scientifically accurately. And in fact, so accurately that the renders that came out of the DNEG render farm appeared in at least two or how many published papers? Two published peer-reviewed science papers discovering features of the light refraction around a black hole by having the power of Hollywood render farms that often scientists don't have access to into this final version that we saw in the movie. And then all of a sudden, that changed what we expect to see for a black hole. And now even Star Trek gets it right. Well, JJ didn't touch either of these, but still, And if Star Trek gets it right, well, we can do better now. So a little like under the hood, the way I used to do this, way back in grad school, I came up with a way of doing a very qualitative way of refracting light, sort of an inverted funnel lens. So if you imagine the camera's over here, you just have a black disc, and you have a funnel going out from it, and you use that funnel as a sort of stand-in for the warping. And just by applying index of refraction that goes out to 1 towards the edges, you can sort of bend light rays more and more as you get close to the disk. I mean, there are limits. It never bends more than 90 degrees. But, qualitatively, at least, it gets you into the ballpark. You can get an Einstein ring. So some of the features are there. And you can do a lot of stuff with this. If you're really careful about where you put your lenses, you can even put two black holes and get a little bit of interaction between the warping of the two. But it definitely had limits, because what we ultimately what we really want to do is a physically correct model. Here's published from a recent paper that really mapped out the light rays around. Light wraps around black holes. So you want something to bend more than 90 degrees. Well, I shifted a lot of my work over to Blender in the last few years, and it has such an active community of people out there who are space enthusiasts, who dive into things and will just throw tutorials on the web to teach everyone how to do better at what they're doing. And I ran into this really clever solution to the black hole problem, which is you basically build a Russian doll of nested spheres that have indices of refraction that are high in the middle and go out to 1 on the edges. You do a little fall off, so you don't use a little bit of Fresnel to make that fall off on the edge of so it doesn't really get sharp edges. And if you do enough of them and you figure out the right range of index of refractions, you absolutely can recreate a good qualitative sense of the light bending around a black hole. And relatively simple node setup that will let you do this. And so I've been able to use this to really good effect now to create sort of test map. These are some animations that I actually produced for an upcoming JPL Black Hole Explainer video that we're going to be putting out during Black Hole Week. So, but you'll see here I've actually also got a little bit of the calculation of incoming, relative to projection, so it gets brighter on one side, something that Interstellar left out because that's the one place Nolan didn't want to go. It was too confusing. Here is a recreation of a tidal disruption event. This is what I call a quasi-simulation. This is done using simulation techniques, but I'm not actually doing a full-on tidal disruption and self-gravity and everything. But what I do is I will turn two simulations, see what happens in an actual simulation, and try to find a quick and easy solution to get something that gets to the 90% mark. And so I do have a differential gravity shearing it, but then I add in a couple extra effects into my simulation to get it to where I want it to be rather than necessarily having the full-on gravity sim. But yeah, so I would posit that from what I've shown you, I hope we agree that now relatively short Blender renders are at least qualitatively in the same ballpark as full general relativistic ray trace black holes simulated using supercomputer clusters. And so given that this has become something that is accessible, I have to comment that when we look back at our bathtub drains and our bowling balls, can we all agree? Never again. And of course, thanks, AJ. On a side note, I wanted to throw in, while we're on the topic of black holes, I just wanted to mention I had an interesting opportunity last year to help Katie Bowman at Caltech in the second EHT result for the Milky Way black hole. And for this one, since Katie's involved in the image processing, for her presentation, she really wanted to introduce the basics of radio interferometry. And this is where I got my start. I was a radio interferometry guy at UCLA, VLA data, Owens Valley data, and part of my thesis presentation was explaining interferometry. But of course, here we had the interesting challenge that it had to be only visual, no mention of Fourier transforms, and do it in less than 30 seconds. So does anyone here work in interferometry at all? Okay, well, you can judge how effective this was. After looking back over decades, I came up with an idea that was actually this isn't even Blender, this is very, very simple stuff, to just establish, if you have two telescopes working together, establish they each see a little part of the picture. And then if you pull them together, they complement each other, fill out the structure, and then if you change the spacing of the baseline, you get sensitivity to different levels of resolution, which when all combined, then give you a full image. And of course, a choice that we made in this, and Katie agreed with, in some sense, this is basically what you have to understand before you can even get to the point where you start to understand a particular interferometer. So we decided, instead of trying to actually just dive right in and make it clear like a very undersampled EHT, let's just go and establish the baseline as a method of scaffolding. Because once you see how this works like in an ideal case, then you can say, but it's so much harder with EHT because we don't have nearly as many telescopes and the baselines don't fully sample, and that the source itself is changing while we're collecting data. But I know, I was kind of proud of this, and I hope if people find this useful, if you're ever trying to explain interferometry, let me know. I'll give you a link to the file. But from black holes, let me go to the other popular topic that we get to, and that's exoplanets. I feel very privileged I've gotten to help explain a lot of science results on exoplanets over the years, because Kepler was out of NASA Ames, and they didn't have a full communications team. And so through JPL, my colleague Tim Pyle and I got to basically participate in most of the Kepler science results over the years. And that was great because Spitzer wasn't ever really designed to do exoplanet studies, but amazingly enough, over its career in space, far beyond any access from servicing missions from the shuttle, through the sheer power of engineering force of will and software updates, Spitzer's pointing position was improved over an order of magnitude, and it became, at the end of its career, the go-to instrument for characterization of exoplanets and even exoplanet discovery. The problem, of course, with exoplanets is the data is some of the least exciting. Isn't that, is that what gets you over the fold on the New York Times? Well, does anyone know what that exoplanet system is? It's TRAPPIST-1. It's a good system, 7 Earth-sized exoplanets. And I will say the data for TRAPPIST-1 is astonishing. It's amazing. When I first got to look at this, when it was still deeply embargoed, super secret, my jaw dropped, because we're used to seeing transit curves that are just barely discernible in the noise, and you have to bin it. And these things are like 100 sigma detections at some point. It was crazy. But even so, I had the scaffolding to understand this. The public does not. And if you want to get above the fold on the New York Times, like we did, finally, yay, Spitzer, we were so hoping someday we would do that. It is the art that captures the imagination of the system that works. And of course, thinking about the check marks of what's the check marks here are really, it's only the relative sizes of these objects are what we knew, and sort of the color temperature of the star, but that was it. It's what captured the excitement of the possibilities that these planets, your-sized planets, represented. Now, I'll admit, sometimes my artist development can be very analog, too. I literally was throwing marbles on the ground when I was trying to come up with an idea for a graphic, because we were going to propose for the cover of Nature for this. And I wanted to do something that was really maybe a little more out of the box than what we classically did with just planet platters and green rings for habitable zones. But it was really, honestly, this photo was what ended up being the thing that motivated me to develop the graphic you see on the right here. And again, going down the checklist of what were the things I wanted to represent in this graphic. First, more or less accurate color temperature for the star. We wanted to illustrate the habitability zone in a way that was more intuitive if you just looked at it. So we show steam when you get close to the star. We show frost and ice when you get far away, and we show drips of liquid water in the intermediate zone. We also like this because it was very gradual, the transition, the sense that it's not just like a hard and fast thing that we can determine at this point. We have correct scalings of the planets. The orbital radii were, I actually did square root scaling on that just so that it would fit artistically, but it still captures the sense of this. And we did have some visual cues, subtle here, suggesting tidal locking, and that the artwork had sort of asymmetries in the two. So that was the things we wanted to get across there. And it did work. It was work for the Nature cover. I'll say, actually, I have to admit, the editor kind of never liked this, and he kept pushing against it. But at the last AAS meeting, he said, yeah, I was wrong. That was a good cover. So he thought it was a little too out of the box for them. This is an example of some of my workflows when I'm just generating the art for exoplanets. I tend to work in nodal procedural systems rather than image map things. And I just love playing with fractal textures, manipulating them. In this case, we were trying to generate a story where you have the possibility of what had been done an eyeball world where you might have a really, really hot side, a really, really cold side, and the possibility of liquid water existing in sort of an annulus around the edge. So, this was a thing that you could actually develop quite easily using procedural systems. And so this is just the kind of stuff I really just geek out in for hours trying to get something that looks cool in the end. And so this is the result that came out in February 2017. But the thing is, we keep learning more about these systems. We keep studying them. And some of the best hypotheses we had for each of these worlds evolves over time as we get new data. And so it was only a year later that we actually updated the entire system. Because, for instance, the world that ended up being most plausible for an ocean-covered world ended up moving from TRAPPIST-D to TRAPPIST-E, so we pushed that there. TRAPPIST-D had the possibility of being a water world, so we switched that to completely water-covered with clouds. Again, one of many hypotheses that were consistent with the data. And the thing is, people have actually asked me, does it get frustrating if you have to redo your art after you release something? And I actually say no. I actually think it's fantastic because the art actually becomes a historical record of the process of science to me. And I love the fact that we get called back to redo things because that means not only are there paper trails for this, published paper trails, but there are trails of art. And for people who really dig into that, then it's a way of telling that story and how science evolves over time. Of course, there are other, even more creative ways to engage people with this. Joby Harris at JPL executed this as part of the really popular exoplanet travel series lines, where they have basically done posters for known exoplanets and really try to viscerally imagine being there, and we had so many really great conversations on telecons with the science team and the communications team. And Joby was on, I was on, and he would come to us with all of these layouts. And I have to say, I just love the iterative processes that these things were designed. And of course, this is way out there, right? But I still just adore this for it places you on the excitement of being on a world and looking up in the sky and being able to actually resolve your neighboring planets, something that's almost unique to the TRAPPIST-1 system. And admittedly, JJ did that in Star Trek 2009. I thought it was stupid, but okay, maybe sometimes it's okay. But talking about exoplanets, no, I should have updated that thumbnail, I think. Talking about exoplanets, I started thinking a lot more about how we do stellar colors as well. And I'm actually working on a result right now where this kind of comes up. But I want to talk a little about this because stellar colors is an area that is not always been done scientifically accurately. And I just did a quick Google search for HR diagrams and stellar color temperatures, and I got a bunch of results, all on authoritative sites. And honestly, every one of these is actually wrong at some level or another. Let's just highlight a couple here. I mean, if we look at this, that's supposed to, that temperature scale in Kelvin, you would think that should be a blackbody scale because it's temperatures, but if it is, it's wrong. I was really shocked. Green stars. There was actually one site that had a green star. And of course, red stars. And the question is, so what's wrong about all of this, and why is this so wrong? And it really got me thinking that, frankly, we have to own this because astronomers for centuries have been really bad at naming things. And if you just think about these commonly used terms in astronomy, I would argue that only 2 of them are right, at all. Blue supergiants, they're blue. Black holes, let's go with, they're black, sure, why not? It's the shadow, no light, that's black. That's as black as you can get. So, but frankly, brown dwarfs, well, it's complicated, but they're not brown. that we know. Yellow dwarfs, let's face it, 65K illumination, isn't that how we define white? That's like canonical white lighting. It's not yellow. Red dwarfs, red giants, they are not red. They are orange. They're red 2500 Kelvin. I think it's about as cold as you get, and that is still very much in the orange range, blackbody spectrum. White dwarfs are hot. They're blue. So we name things badly. And we do our illustrations to follow the names rather than the actual reality, because of course, these are all color-coded, colder to hotter through blackbody temperatures. And so we end up getting this, this effect that to exaggerate this and to adhere to the nomenclature, we force pictures of the sun to be yellow, even though it isn't actually yellow. Though, I mean, again, on the right day with enough dust in the atmosphere, catch it before sunset, there are times it can kind of look yellow, but honestly, the days when I look outside and I see everything has a golden illumination, I think, oh, that's cool, that's unusual. I run out and I look at it, because that's not what the sun looks like normally. We tend to over-exaggerate the colors up here on the blue spectrum. This is very typical of what we might do. And of course, I mark a little outline around those things. Well, but once you get under 2,500 Kelvin, you're not even talking stars anymore. You're talking about brown dwarfs. So, of course, we can absolutely go in and just do it realistically. But if you're really doing it realistically, there's also the t to the fourth law that you have to deal with in terms of the overall luminance of them. And to put everything on the same scale gives you stuff that's really blown out on one side, almost impossible to see on the other. But, fine. Let's at least take that, renormalize the exposures, and we can get something like this. Now, these are actually rendered to accurate black-body colors. And working in Blender these days, it's actually lovely and easy for me because there's a shader node that actually does that math for me. I don't even have to look it up in a table. It's available to me in the shader tree. But it turns out that it's kind of hard to sell this sometimes. And even with accurate colors, it doesn't always come out accurate in your renders for a lot of reasons. So up until this year, Blender used a transform to get from RGB values of color into an actual final rendered image. This transform is called filmic. And if you've ever worked at all with color, you know that there is a very indirect path to go just from an RGB value to what we consider to be an absolute color on the other end. We have gamma functions. We have screen color spaces. We have, Adobe RGB, sRGB, all of this, right? And then it even gets harder if you, say, up the exposure, like I want to do for a star, to bloom it out and use the glare effect to sort of suggest the brightness. The filmic transform had a feature they happily had engineered into it to try to capture overexposed images in a way that is akin to an HDR image. But this had an effect that kind of was frustrating to someone who's been crusading against yellow stars, that it turns all the orange stars into yellow-looking stars for the most part. And so it's kind of ugly. But to my thrill, this year, they actually introduced a new transform in Blender to change the way that you do this mapping, particularly for overexposed objects. This new AGX transform now actually does this wonderful job of letting the image look exposed, but not losing the fundamental color tint of the individual objects. So we can preserve the sense of color temperature. More of the color spills out into the glare effect around it, which is nice. It's in the same way that when you look through, get photos of stars, you tend not to see the color of a bright oversaturated source unless you defocus it a little, and you get a little bloom to the side. So this is great. What's interesting, though, is even working with astronomers, I find I am asked to take a star of a known color temperature and make it look red because it's a red dwarf. It should be really red. And I get it. There's an expectation sense of, you want to say, our star is really cold and we want people to appreciate it, so make it look really red. But at least I found a way to be at peace with myself when working with my peers on this to do things. When I'm asked to make a star redder, this is actually from the project I'm working on right now. I went into Blender and I rendered out this palette of stars, and I included the color temperatures that go with that. And I synthesized it. Okay, tell me what temperature you want me to show your 3,300 degree Kelvin star as, and I'll do it. So I think they landed on 2,400 Kelvin, but I made them say the number. I had to say the number. It's like, tell me how inaccurately to render the data. So I'm good with that. It's like, at least we're all aware of what we're doing. Be upfront about it. So just to preview, this is this will go out probably in a week or two, but I just wanted to show. This is the actual artwork I was working on for this, and I have to admit I have an inordinate amount of fun in Blender just coming up with procedural systems to get really cool-looking planets. But it's like I can live with that. That's at least this doesn't look like the deep, lurid red orb that we see so often in exoplanet art with a planet next to it illuminated by a white light source, which always just drives me completely batty. So this is good. We can live with results like that. So I wanted to just wrap up then by and open it to questions, but mention a couple of things here. If you like astronomy images and you want to find astronomy images, there's a project that I work on under NASA's Universe of Learning, which is a project funded by NASA to do kind of outreach and engagement with the community. Astrophysics.org, we actually have the data sets from all of the major NASA and ESO, NORLab, NRAO observatories. We've all spent years agreeing on this common metadata format for the public images. They all get tagged to this, and we pull it into Astropix, and you basically get one-stop shopping for all of this. We just last week rolled out a new UI for it, a much easier to use simplified UI where you can type in your object name, it'll look up the coordinate, and we do all the searches like any other archive by coordinate. We also have a growing archive of artwork that's showing up there too for illustrating purposes. So encourage you to check out Astropix, and if feel free to send us feedback. We're really looking for information from the community of what we can do to make the site work better for you. The only thing I'll say is what I can't do is change the actual captions and text, right? Because we are simply aggregating and making everyone else's work available in one spot. And also, for anyone who is actually really interested in visualization, astrophysics visualization in particular, we've been spending a lot of effort in the last few years to try to reinvigorate what had been a fairly engaged community of practice back in the early 2000s, and in some ways it was actually kind of shut down around 2011 when NASA had all these travel restrictions and we stopped having annual meetings. But if you scan this QR code, we have a little sign-up form, and it's not too active yet, but we put out a bi-monthly newsletter with a few tidbits of interest. We have a Google group it's very low traffic right now, but it's a place to reach out if you have a question or even if you've done a really cool visualization, you want to sort of share it with peers. That's what we want to do here. We run quarterly virtual events where we panel discussions. We bring in people to just sort of present on topics. So it's a place where we're really trying to encourage people to be engaged. We also have been doing 4-hour visualization workshops at AAS meetings in January. So Frank Summers and I at Space Telescope co-run that with Kim Arcand out of Harvard. So if you want to engage more, please go fill out the form. We'll add you to the lists, and we can keep the conversation going.
Question for Thank you very much for this excellent talk. Obviously, the visuals were awesome. But I'm wondering so you mentioned really early on with both visualization, and I found the same to be true in tons of outreach, that sometimes you need to accept that you're going to have some bits that are inaccurate, literally untrue, to make sure you're giving a cogent picture to the audience. How do you address, or what strategies have you found successful for addressing those inaccuracies? Because I often find that that's where I stumble over my words when I'm well, technically, when I say XYZ, this isn't literally true, but, we're going to say it's true or good enough. Does my question make sense?
Yeah, no, that actually makes sense. And I may think about that because it's something I don't think I've considered explicitly. Also because often I'm not actually engaging with people directly, right? I'm producing things that goes out. At most, sometimes I will actually write up a caption to go with an illustration, and then by the time it gets edited down, it has very little content left. And I'm I wish you hadn't cut all that out before you released it, but whatever. But honestly, I think it's just, I think there's just an authenticity of simply saying, you can just really lean into it, right? I don't think you have to make excuses and back up I know technically you're wrong, right? You can just sort of lean in. Well, so we've exaggerated scale here, but really we've just done that for clarity. And particularly if you are in an outreach kind of scenario where you are working not so much, more towards that side of that initial audience spectrum, people who are engaging with you, right? You have a chance to just sort of lean into it. Okay, here's the visualization, so we've exaggerated a few things to make it a little clear, but we really want you to be able to see this, right? I would say lean into it as a positive rather than apologizing for a negative, because then you really are still pulling focus on what you want them to know while acknowledging that there is exaggeration in it. Huh. Cool question.
Yeah, thank you for the talk. My question is, I'm sort of wondering what's next for the field. Like, are there any major hurdles or problems that the field is dealing with in terms of representing, XYZ object or communicating XYZ ABC, term? Is there, what's next for the field if you had power to change something in the field?
Oh, power to change. Well, okay, there are a couple threads that I can pull on that, because that goes, there's a number of directions. But I actually was just having a conversation right before my previous talk. The one area of where we're going in terms of astronomy, where I think we're going to have to really think hard how we communicate this visually, is like dark energy. Anytime something comes up on dark energy, I just kind of quietly go to the corner and I cry for a few minutes. And then I come back, sure, let's come up with something. And, and unfortunately, off and on dealing with that over years, I haven't really come up with anything more creative than I'll color gravity green and I'll color dark energy purple. But, I don't know. That's my color. But another aspect of what you asked, I might say, in terms of a challenge to like astronomy visualization and to so many things, is AI and its role in what we do. And I will say, at least in the little experiments I've done with generative imagery so far, I'm kind of not yet worried about it displacing what we do, because the one thing that it is not great at is taking very specific instructions, right? And the wealth of imagery it has to draw on for astrophysical phenomena is so small compared to the way it's easy to put, a political figure on a horse, but it's like to actually, it doesn't have, the inputs will never have like accurate evaluations, which is a good black hole versus a bad black hole. There's a lot about technical illustration I think is still protected from that kind of thing for the time being. Though I will admit it can be very handy if you're just trying to do like light visual engagement stuff. I did a project with George Jurgovsky at Caltech where they needed some illustrations just to go into a white paper on how to look for technosignatures around other stars, just very speculative. And we generated a lot of fun stuff that just was suggestive of networks and AI computation methods and stuff that like worked for incidental. But it really, I wouldn't have relied on it to do a very specific thing of like, oh, show me a Dyson sphere or something like that.
Thank you.
So early on, you showed that early galaxy that you said was airbrushed. I was curious what the transition was like from physical, like paint on canvas media, to digital, especially with like animations.
That was an interesting transition, because I did, like I said, artwork was sort of my relief valve in grad school and everything. But I will say that when your relief valve also involves a lot of frustration when the airbrush clogs up and all of a sudden the clog clears and poof, all over, and then it drips, and like, okay, let's make that a dark cloud because I have to paint over that. Once I started playing with Photoshop and I realized, wow, when I'm done with Photoshop, I hit Command Q and it's done. I don't have to spend 20 minutes cleaning my airbrush. It was a pretty quick transition for me, actually. And I do actually lament it. Like the last piece I ever airbrushed is still in a frame on the wall in my living room, just to remind me there was a time I did physicality, and there were one-offs. But yeah, it was it somehow. It was a sense of loss, but also like it's easier in so many other ways.
Kind of linked to Liam's question, when you're working for places like JPL, do you ever get specific instructions or guidelines for inaccuracies that they want you to make, or that they'll let you get away with? And kind of also, how often are you able to put that in the final writing, maybe down at the bottom of the page, for here's what little approximations we made?
Yeah, no, let me think about that. I would say I'm usually the one who's more worried about inaccuracies than JPL, and I mean, in a sense, that's my job. Because I have this kind of unique position as astronomer and illustrator. That's actually one of the things I actually bring to the table. There is sometimes a negotiation with the principal investigators of a result, like why might we choose to do something inaccurately, because they might actually push on it. The JPL office, the media team there, a lot more of the pressure I get from them has been more of that, oh, this is something we don't expect, and let's just do it the way people expect, even if it's not accurate. So I think that's kind of more of what I get there. But like I say, it generally isn't like a huge issue, because if you initiate this process by getting everyone talking on the same call, it is so much easier to work through this than trying to do it in an email chain. I mean, just stab me with a knife if I have to like do a major release and everyone's in different time zones and we only are communicating by email. It is so impossible to like make progress. Whereas if you just get people talking, we can all like find the sweet spot that makes everyone happy. And that's where we get centered on the triad, right? It's like you can just do that really quickly if you just get to talk to people.
This is similar to Brock's question, but I'm like really interested in the procedural generation kind of stuff, and I was curious. You said art was like a hobby. Are you self-taught, or did you learn it on the job? Like, this Blender is quite different than.
So I was, I took 3 years of art in high school, and I had a sort of détente established with my art teacher where, okay, I'll do your negative space drawing of the stupid chair 1 week, let me do a nebula next week, right? But I was engaged, so she gave me the school. I took a little bit of art in college, but beyond that, really it's been mostly kind of self-taught. It's like, again, it was my go-to to get away from the research, and I jumped onto 3D imagery really early. There's an old program that came out for the Mac called Bryce 3D that I just was amazed when I first saw it. It was all about making landscapes, natural landscapes with clouds and atmosphere, and I loved the fact that it just gave you a simple tool to make a complete picture, not just build a model of a tire. And so that was, and that kind of software is hard to. There's anything really like that anymore, that just like leads you right in. I think people. The only software that does that now is generative AI, but then that takes all the fun out of it. It's like, oh, I'm really good at word crafting a prompt. I mean, like, oh, I'm sorry, that just isn't that fun.
Did you have a hand in the Eyes on Exoplanet art? And if so, or if not, have you ever considered working with like more interactive media?
Right. In fact, I do. When Eyes on Exoplanets especially when you have new discoveries that are connected to a press release, I'll actually give them equirectangular mapped planet maps for the ones that we do for the release. To be honest, we haven't done that for a while now, sadly, but certainly like the TRAPPIST planets were all like, for instance, in Eyes were built on that. So whenever possible, we try to accommodate that. And sorry, what was the second part of the question? It was just working more with interactives. I love interactive systems, and I'll say one of the projects when we still had funding under Spitzer and we had a little more freedom to just sort of do projects of passion and not necessarily like funded individual from projects, we did a VR experience called Exoplanet Excursions. It was for PC VR, so it was still tethered. It was before the Quest came out. And we used all the assets that we had generated for the Spitzer press releases to make a non-interactive but immersive 3D fly-through to like actually, because we loved TRAPPIST because this idea that you could actually do an exoplanet system with the planets to actual scale and you still saw them was like a huge part of that story. So I loved that we could just basically do something that led you through as if you were actually there to all these worlds and establish like that context. We even did a VR project after that. We attached to it where we did the Spitzer telescope and we let you sort of learn how Spitzer observes, and we gave you targets and you had to like manipulate Spitzer in its zone of visibility, which was again uniquely suited to immersive because of the nature, like it's this band in the sky, and it's so hard to do in a video, but if you can just plop someone in, they actually get to experience that. But I am hoping to do more immersive work. I know Blender makes it really easy to render out 3D 360 movies that you can then view in headsets. So. But interactive takes so much more time as soon as you do that element. Immersive, is the first step, and that's easier, but interactive, like, that takes you down the whole development cycle. And we've never had the cycles even to adapt exoplanet excursions to the Quest for standalone, unfortunately, because it's just the huge amount of development time for that.
One more question, and then we'll be around to.
Sorry, I just answered. I give very long answers.
I guess my questions are information seeking. When you are, like, how much of your time do you spend reading, catching up on the literature? And because you have to know what temperature things are and stuff like that. So keeping up on the literature. And then also, do you go around looking to see how other people have created images before you create your own image? So what kind of information seeking behavior do you do in your work?
Okay, right. That's interesting. Let me think, because so on the science side, I actually honestly I don't keep up. I let myself go with I'm really good at telling you the science of something we did a press release on, but anything ancillary to that, it's like, oh, there was a paper on that, cool. But for my from the visualization part, the skill sets for doing the 3D work, I spend a tremendous amount of time digesting like YouTube videos and tutorials. I've actually found that motion graphic artists, I learn a tremendous amount from people who are just doing like looping motion graphics works for for like running behind a music video or something. The techniques they use, I realize so many of them are actually applicable, like visualizing flows along vector fields. It's like so many MoGraph people do that to make something look cool, and I'm like, oh, you could take that technique and then attach it to data, and then you're actually illustrating a science result. But yeah, I will say I spend a lot of time just on the side, just like if a new Blender tutorial pops up, I look at it, because the problem is when a release comes up and we have a tight deadline, I really don't have time to suddenly spend a week figuring out how to do a thing I don't know how to do. But if I at least have kept up on a lot of interesting techniques people are doing for things way outside of Astroviz stuff, I know I'll have a memory like, this is a thing. Oh, I can use that, something I saw 6 months ago, and it gives me kind of a shortcut to get back to that piece and run it up. So yeah, that has been really critical to me since I switched to Blender. Because when I was on Lightwave, I was just kind of used to it, and there weren't a lot of things to go out there, and I kind of stagnated. I didn't have a lot of opportunity to pivot to like whole new ways of going at it. Blender's really opened a tremendous amount of potential for me, and it's wonderful because anyone can get it for free, and I can go. Actually, I have a goal soon because I've gotten so much from the community. I want to actually start making astronomy visualization how-tos to kind of get back to the community, and because there's so many people interested in astronomy but just come at it, I want to make a cool nebula. And I figure maybe there's a kind of a niche I can go in of looking at it as an astrophysicist, and like here's how you actually kind of make it with a little more authenticity. So I'll take that as a kick to like get to that really soon. And actually I'm going to, and in terms of also building out my own skills, next Thursday and Friday, the first BlenderCon outside of Europe is going to be in Hollywood, like 7 miles from my house, so I figured I really needed to go to that. So I'll get a chance to see like a very broad set of like what people are doing with Blender when I'm there.